Hello and welcome back, everyone. All right, now, seniors, let's take this exercise one after the other. This is the exercise where we did some examples on measurement of heat, specific heat capacity, and heat capacity. The first question here says a tap supplies water at 26 degrees Celsius, while another supplies at 82 degrees Celsius. If a man wishes to bathe with water at 40 degrees Celsius, what is the ratio of the mass of hot water to that of cold water? Okay, let's say this is hot water. Let's say this is hot water. Let me take it one by one. Let's say this is hot water. And this is what? Cold water. Hot water is at 82 degrees Celsius. Let's just separate the two. Let's say this is a container, hot water, container, cold water. We now want to combine it. The hot water is at 82 degrees Celsius. Cold water is at 26 degrees Celsius. Let's be sure these values are correct. Okay. We now want to mix the water in such a way that at the end of the day, we fill our bucket with water that's at 40 degrees Celsius so that we can easily bathe. 40 degrees Celsius. What this means is very simple. You can notice that water at 40 degrees Celsius is not as cold as water at 26, and it's not as hot as water at 82. So what happens in this mixing is that hot water loses some heat. Hot water loses some heat called heat lost by hot water. Now, the cold water at 26 here gains some heat called heat gained by cold water. To come to 40 degrees Celsius mixture or Celsius final temperature, hot water will lose some heat, cold water will gain some heat. So they now attain thermal equilibrium where both of them have the same temperature, 40 degrees Celsius. So heat lost by the hot water is equal to heat gained by cold water. Because you are going to take a small amount of hot water and mix it with some amount of cold water. The heat lost by the hot water will be gained by the cold water that you mix into this container. You are mixing the two. So let's go. Heat lost by hot water is equal to heat gained by cold water. Now, heat lost by hot water will be the mass of hot water times the specific heat capacity of water times change in temperature of the hot water. Also, the heat gained by cold water will be the mass of cold water times the specific heat capacity of water times the change in temperature of cold water. The cold water will increase in temperature from 26 to what? From 26 to 40. The cold water will increase in temperature from 26 to 40, and the hot water you take will decrease in temperature from 80 to 40. So, let's continue. So the heat lost by hot water is equal to heat gained by cold water. I want to take this one by one. Now, heat lost by hot water is the mass of the hot water. Now, okay, I've written that already. CW, we cancel CW on both sides because it's referring to the same quantity, specific heat capacity of water. So you have mass of hot water times change in temperature is equal to mass of cold water times change in temperature. Exactly. So mass of hot water, the temperature of hot water will decrease from 82 to 40. That of cold water, the cold water you take, its temperature will increase from 26 to 40. But temperature is a scalar quantity, so we still subtract in the right way. We still subtract the smaller value from the bigger value. So at the end of the day, you will get mass of hot water times, this is 38, 42, Mass of hot water times 42 is equal to mass of cold water times what? 14. Now, also, this means 14 here 1, 14 here 3. So, that means that 3 times mass of hot water is equal to what? 1 times, this is 14, 14, 1. 1 times mass of cold water. So, now, remember that in math, there's something we do in math. In mathematics, A times B in math is what? Is C times D. When A times B in math is C times D, we have written this in straight form. If we want to write it using fractions, we are going to do A over C is equal to B over D. You will not do A over C is D over B. That will be wrong, because cross multiplication will not give you this back. But you do A over C is equal to D over B. I just take it A over C is D over B, not B. A over C is D over B. That's the correct thing to do. So that when you cross multiply, you get AB is equal to CD bar. Just like saying 4 times 6 is what? 2 times 12. You know, here, if I want to use fraction to express this, I should say, I'm supposed to say what? I'm supposed to say 4 over 2 is 12 over 6. I'll say 4 over 2 is 12 over 6. If I write it in any other way, it will not be correct. So, this will tell you that this means that the mass of, the question says we should find the ratio of the mass of hot water to that of cold water. So mass of hot water over mass of cold water, that's this over this, is equal to 1 over 3. We will not say mH over mc is equal to 3 over 1. That will be wrong. We should correctly say mH over mc is equal to 1 over 3. So you take it left over right is equal to right over left. Exactly. So mass of hot water over mass of cold water is equal to what? 1 over 3. Therefore, ratio of the mass of hot water to the mass of cold water is 1 to 3. So you just take a little hot water and add 3 times of that mass of cold water. Exactly. Let's go to question 2. It's a simple exercise. We'll finish it now. A tap supplies water at 30 degrees while another supplies water at 86. It's a van which is to buy. So number 2 is the same as number 1. You do that yourself. Question 3. 2 thermos flasks of volume Vx and Vy are filled with liquid water at an initial temperature of theta degrees Celsius. 2 thermos flasks. Okay, let's draw the flasks like this. 2 flasks. Okay, filled with liquid water at volume Vx and Vy. The question says, okay, the 2 liquid waters are temperatures 0 degrees Celsius. 0 degrees Celsius. The question now says, after some time, the temperatures were found to be theta x and theta y, respectively. The temperatures were found to be theta x and theta y, respectively. Okay, the question says, given that Vx over Vy is 2. Okay, given that Vx over Vy is 2, which is the same thing as 2 over 1. And theta x over theta y is 1 over 2. Theta x over theta y is 1 over 2. The question says, what is the ratio of the heat flow into the flasks? What is the ratio of the heat flow into the flasks? Okay. What this means is very simple. Ratio of heat flow is change in heat in X over change in heat in Y. Change in heat in X will be mass of water times specific heat capacity of water times change in temperature. Mass of water, let's assume the mass is directly proportional to the volume. So it will be Vx, which is volume of liquid in flask X, times specific heat capacity of water, times change in temperature. Change in temperature will be theta x minus 0. Also, so let's now write that in full. That means heat change in X is Vx times specific heat capacity of water times theta x. Also, without writing stories, heat change in Y will also be Vy over specific heat capacity, Vy times specific heat capacity of water times theta y. Okay, if we want theta, if we want delta hx over delta hy, what we do is just substitute. That means we can say heat change in X over heat change in Y is equal to what? Vxcw theta x all over vycw theta x. So, theta y, cw theta y. But if you look at this ratio, theta x over theta y has been given up here as 1 over 2 here. And what? Also, Vx over Vy has also been given as 2 over 1. So that means for Vx over Vy, I'll write 2 over 1. For Vx over Vy, I'll write 2 over 1. Then Cw will remain. Then for theta x over theta y also, I will write 1 over 2. So at the end of the day, you get the same thing. 2 we divide 2, 1 we divide 1. Cw. So your answer is 1 over 1. So the ratio of heat change in both flasks, delta hx over delta hy. The ratio of heat change in both flasks, delta hx over delta hy, is 1 over 1 or 1:1. That answers question 4. Question 3, I mean. Let's go to question 4. In question 4, it says a tap supplies water at 25 degrees Celsius, while another supplies water at 75 degrees Celsius. If a man wishes to bathe with water at 40 degrees Celsius, what's the ratio of mass of hot to mass of cold water he must mix? So, there's a bowl here supplying water at 25 degrees Celsius. Another bowl or tank supplies water at 75 degrees Celsius, or tap, you can call it whatever you like. So you want to mix the water such that you get water at 40 degrees Celsius. That's easy. When the two waters come together, the heat lost by this amount you take from cold water, this is the cold water, this is the what? Hot water. The heat lost by what? By the hot water is equal to the heat gained by the cold water. Exactly. So heat lost by hot water is mass of hot water times specific heat capacity of water times its change in temperature. Also, heat gained by cold water is mass of cold water times specific heat capacity of water times change in temperature of water. So, in essence, you don't know the masses taken, just say mass of hot water times Cw times what? 75 minus 40 degrees Celsius. Because as you can see, hot water will come from 75 to 40. It will lose heat from 75 degrees Celsius to 40 until it cannot give out heat anymore. When the liquid that is giving out heat to, when the liquid to which it is giving out heat has also gotten to 40 degrees Celsius, and that's what we call thermal equilibrium. Two objects, heat will flow between two objects that are hot and cold until thermal equilibrium is reached. So when the two waters are mixed, hot water will continue to give heat to the cold one, and the cold one will also continue to accept heat from the hot one until both of them attain the same temperature and thermal equilibrium is reached. So at thermal equilibrium, there will be no temperature difference. There will be no temperature difference or temperature gradient. And so heat will stop flowing between them. So take note of that. So the hot water will lose heat from 75 to 40, while the cold water will lose heat from 25 to 40. So we subtract the smaller temperature from the big one. So at the end of the day, if you look at this well, CW, we divide CW, you don't have it there anymore. And that gives you what? Mass of hot water times 25 is equal to mass of cold water times 15. Divide also 5 here, 5, 5 here, 3. You understand what I'm doing? 5 in 25, 5. 5 in 25, 5. 5 in 15, 3. I'm not supposed to cancel my steps, so it's a good habit to just always do it in your mind. MC. We are looking for ratio. So this gives you what? What does this give you? 5 times mass of hot water is 3 times mass of cold water. That means mass of hot water over mass of cold water mixed will be 3 over 5. Can you see where I did it here? You do left over right is equal to right over left. Can you see that again? Let me do that again. You do left over right is equal to what? Is equal to right over what? Left. So that's the correct order. Therefore, the mass of hot water, ratio of the masses of hot water to cold water you must mix is 3:5. So that ends that. I will not answer this kind of question again in this exercise. You did the rest yourselves. Let's go to question 5. Hot water at a temperature of T is added to twice that amount of water at a temperature of 30 degrees Celsius. I'm going to do this. Hot water at a temperature of T. Hot water at a temperature of T. Let's just put T inside the container. T degrees Celsius. Hot water at a temperature of T degrees Celsius is added to twice that amount of cold water at a temperature of 30 degrees Celsius. So we will call this cold water, but the mass of hot water added is X. You understand? Let's call this mass of hot water. Let's call this mass of hot water, and mass of cold water will be equal to 2x. So because the amount of hot water added, the amount of cold water added is twice the amount of hot water added, and the two are mixed. Okay, the question says, if the resulting temperature of the mixture is 50 degrees Celsius, calculate T. After mixing, we got a sample of water that's at 50 degrees Celsius. So we now want to calculate T. Let me take the question again. Hot water at a temperature T degrees Celsius is mixed with cold water at a temperature 30 degrees Celsius. Can you see that? Now, the question says hot water is added to twice its amount, you understand, of cold water. So that means if the mass of hot water is X, the mass of cold water mixed with it is what? 2x. It's as simple as that. Twice its amount. So if X is its amount, the amount of cold water mixed with it is what? 2x. So that solves the problem. We now do the same thing we always do. Heat lost by hot water. Let me just do this for that. Heat lost by hot water is equal to heat gained by cold water. Heat lost by hot water is mass of hot water times specific heat capacity of water times change in temperature of hot water. Heat gained by cold water is mass of cold water times specific heat capacity of cold water times change in temperature of cold water. So I think that will make sense. So we just use our x times this will go. They are both the same on the left and right. So you can cancel seawater, seawater. You understand? That's like dividing both sides by specific heat capacity of water. This will take this, this will take this. So that will not be there again. Do you understand what I've just said? That step is like dividing both sides by specific heat capacity of water. This side too, if you divide by specific capacity of water, the specific heat capacity of water will not be on both sides again. So that tells you mass of hot water times change in temperature is mass of cold water times change in temperature. What's the mass of hot water? What's the mass of hot water? X. What's the change in temperature? It should go from T to 50. That's a decrease. So I'm going to do higher temperature minus lower temperature, because the temperature of the hot water will decrease from T to what? 50 degrees Celsius. Hot water will continue to lose heat in the mixture until it gets to 50 degrees Celsius. Cold water also will continue to gain heat in the mixture until it gets to 50 degrees Celsius. When both samples now get to the same temperature, 50 degrees Celsius, you understand? Heat flow will stop because there's no temperature gradient. You understand? Heat flows in the direction of temperature gradient. So mass of cold water is 2x. Temperature change, I can put times here if I like or leave it out. So temperature change will be, cold water is increasing in temperature from 30 to 50. So the difference will be 50 minus 30. We always do temperature difference in the order to give us a positive answer. So x, we divide x on both sides. Can you see? There's x here, there's x here. Both will divide each other. So what you have left is T minus 50 is 2 times 50 minus 30. So 2 times 20 is T minus 50. What does that give you? T minus 50 is what? 40. T is 40 degrees Celsius plus 50 degrees Celsius. So the temperature, the initial temperature of the hot water was what? 90 degrees Celsius. Take note of that question. You can pause and replay if you need to see it more than once. Okay, that's number 5. Let's continue. It's a long exercise, but we'll finish it. Number 6, 400 grams of cold water is added to 200 grams of hot water. 400 grams of cold water is added to 200 grams of water at 70 degrees Celsius. So water at 70 degrees Celsius is definitely hot water. If they are properly mixed and the temperature of the mixture is 30 degrees Celsius, calculate the initial temperature of the cold water. This is the same as number 5. So, but I'll just do that for you. Cold water, 400 grams. Cold water, 400 grams. We don't know its temperature. Let's just put theta here. Then hot water, 70 degrees Celsius is its initial temperature. Only 200 grams was mixed. At the end of the mixing, both came to what? Both came to 30 degrees Celsius. The question says we should find the temperature of what? Temperature of the cold water. This one. So this is cold. This is what? Hot water. That's simple. We do the same thing. Let's use blue here. Heat lost by hot water is equal to heat gained by cold water. Heat lost by hot water, let me see, 400, 200. Okay, 30. Heat lost by hot water is mass of hot water times specific heat capacity of water times change in temperature of water. Heat gained by cold water is mass of cold water times specific heat capacity of water times change in temperature of cold water. So that means mass of hot water, 200 grams, times specific heat capacity of water. Okay, as we always do, this will, cancel on both sides. So you have, what do you have left? What do you have left here? What you have left is, if you divide both sides by CW, you will have mass of hot water times delta theta, change in temperature of hot water, is equal to mass of cold water times change in temperature of cold water. This must have divided this. So you will now write that in the next step. Mass of hot water is 200 grams. Change in temperature of hot water, it must decrease in temperature from 70 to 30, or it decreased in temperature from 70 to 30 in the mixture. But the cold water's mass was 400 grams, and the cold water increased in temperature from the initial theta we don't know to 30 degrees Celsius in the mixture. You understand? Let me show you that from here. When the two samples are mixed, or when the two masses are mixed in this container, the cold water will increase from theta to 30 in temperature because it's gaining heat from the hot water, which decreases in temperature from 70 degrees Celsius to 30 by losing heat. So take note. Our next step is 200 times 40 is equal to 400 times theta minus 30. So what does this give you? 200 here 1, 200 here 2. So 1 times 40, 40. Let me just try and write as neatly as possible. Then 2 times what? Theta minus 30. This will give you 2 theta minus 60. This will give you 40. So 40 plus 60 is what? 2 theta. Is that clear? So 100 is equal to 100 is equal to 2 theta. What does that give you? 2 theta is 100. Theta is what? Theta is 100 over 2. Theta is 50 degrees Celsius. This is not looking okay. Let me see what the problem is. I think I've made a mistake. Okay, I've seen my mistake. The temperature of cold water increased from theta to 30, not from 30 to theta. So this side is not correct. That's why my answer is not correct. Sorry for that mistake. So the temperature of cold water increased from theta to 30. The change in temperature of cold water would be 30 minus theta because it's coming from theta. It's coming from a cold value theta to a higher value 30. So this should be 30 minus theta, not theta minus 30. So this is 60 minus 2 theta. Exactly. So more correctly, I should be doing 2 theta. If you bring 2 theta to the left, it will become positive. It will become positive 2 theta. Then you take 40 to the right, it will become 60. 60 minus what? 40. So 2 theta is 20. And what? Theta is 20 over 2. Theta is 10 degrees. Theta is what? 10 degrees Celsius. So that means the cold water increased in temperature from theta to 30. I told you that we must always do our subtraction such that the temperature difference is positive. So this is the lower temperature. This is a higher one. water was colder than 30 before. So change in temperature for water will be 30 minus theta. But for hot water, for cold water, it will be 30 minus theta. But for hot water, it will be 70 minus 30. So that was the mistake that we needed to correct, and that will be right too. So always maybe wait a second to listen first before writing, just in case. Number 7. Two liquids P at a temperature 20 degrees Celsius and Q at a temperature 80 have specific heat capacities 1 and 1.5. Okay, let's take that one by one. Liquid P. Let me just draw a container. Liquid P is here. Initial temperature. We will write it down. Then liquid Q is here. Initial temperature, we write it down. What's the initial temperature of liquid P? 20 degrees Celsius and Q 80. Initial temperature of Q 80 degrees Celsius. Initial temperature of P 20 degrees Celsius. The question says they have specific heat capacities 1 and 1.5 joule per kilogram per. So C of P, specific heat capacity of P, 1 joule per kilogram per degree Celsius. That of Q, 1.5 joules per kilogram per degree Celsius. The question also says, if equal masses of P and Q are mixed in a large calorimeter, what is the equilibrium temperature? Okay, so mass of P is M, mass of Q is also M, and both were mixed. When both are mixed, because they are not at the same temperature and their specific heat capacities are not the same, heat will be lost by P or gained. Heat will be lost by Q or gained. So let's just say heat change in P will be equal to heat change in Q. Whether loss or gain, heat is a scalar quantity, so we don't really care about which one loses or gains. Let's just know that the change will be the same. Anyone losing heat, you understand, the amount of heat it loses will be equal to the amount of heat the second one gains. So heat change in P is mass of P, which is M, times specific heat capacity of P, times change in temperature of P. Let's see if we have their final temperature. Okay, we are looking for the equilibrium temperature, theta. The two of them mixed and came together, and we are looking for their equilibrium temperature. Let's say final temperature, theta. You understand? Or let me just write theta straight. We are looking for their equilibrium or final temperature, theta, after mixing. So that's a pretty simple question. Let's just take it one by one. Heat change in P is mass of P times specific heat capacity of P times change in temperature of P. So, okay, as you can see, Q is at a very high temperature, P is at a lower temperature, much lower. So definitely Q will lose heat and P will gain heat. So that means P will go from the heat change, that means the temperature change in P will be theta minus 20, while the temperature change in Q will be 80 minus theta, because P will increase in temperature from 20 to theta, while Q will decrease in temperature from 80 to theta. So take note of those differences. The temperature of P will have to increase from 20 to theta. So if we want to do final minus initial, we'll be doing theta minus 20 in the right order, because theta will be bigger than 20. But in Q, the temperature will have to, decrease from 80 to this theta. The temperature will have to decrease from this 80. The temperature will have to decrease to theta. So we are supposed to do 80 minus theta. So let me put that here straight. Theta minus 20, then Second one, heat lost by Q will be mass of Q, which is the same M, times specific heat capacity of Q, times change in heat or change in temperature of Q is now AT minus what? AT minus theta. So take note of that, because its temperature will drop from AT to theta. So if we put the two together, what do we get? M will cross M on both sides. We get Cp times theta minus 20 is equal to Cq times AT minus theta. That will give us Cp, 1 joule per kilogram per Kelvin, times what? Theta minus 20. It's not compulsory you write these terms. You can just write your one. Cq is 1.5. Not compulsory you write this multiplication sign. 80 minus what? Theta. So let's do that together. Theta minus 20 is 1.5 times 80. That's 120 minus 1.5 theta. So if we put the two together, theta plus 1.5 theta is 120 plus 20. What does our final temperature give us? Things are getting too dark, so let me change this. This is like 1 theta plus 1.5 theta. That's 2.5 theta is equal to 140. Theta is 140 over 2.5. You press your calculator, you get your answer for the final temperature of the mixture of the two liquids. Temperature is in degrees Celsius. So let's go to question 8. Hot water added to 3 times its mass of water at 10 degrees Celsius, and the hot water is added to 3 times its mass of water at 10 degrees Celsius, and the resulting temperature is 20 degrees Celsius. What's the initial temperature of the hot water? Okay, this is simple too. I'll run through it very fast. Okay, number 8. Let's say mass of hot water is X. 3 times its mass of cold water will be 3X. Initial temperature of hot water, we don't know. Initial temperature of cold water, we know to be what? 10 degrees Celsius. The question says, okay, and the resulting temperature of the mixture is 20 degrees Celsius. Final temperature of cold water, 20 degrees Celsius. Final temperature of hot water, 20 degrees Celsius also, after mixing. This must have happened after mixing. Both of them came to a final temperature of 20 degrees Celsius. I might as well clean this to show that both came from their initial temperatures to this final temperature. So let's leave it like that. I think that's better. So what do we do to get our answer? We are going to go say heat. This is hot. This represents hot water. This represents cold water. So heat lost by hot water should be equal to heat gained by cold water. This is mass of hot water times specific heat capacity of water times change in temperature of hot water. This will be mass of cold water times specific heat capacity of water times change in temperature of cold water. Mass of hot water here is what? X. Mass of hot water here is X. CW must have divided CW. So change in temperature of hot water will be what? Will be, let's just call the initial temperature of hot water, let's call it theta. So change in temperature here will be theta minus 20, because hot water will be decreasing from this theta to 20. You understand? It is cold water that will be increasing in temperature from theta to what? To 20. This one will increase in temperature from theta to 20, while this will decrease in temperature from this one will increase in temperature from 10 to 20, or from theta 1 to 20, while this will increase from theta, while this will decrease, from theta to 20. So the change in temperature here should correctly be theta minus 20 for hot water. On the side of cold water, it should be 20 minus 10 for initial and final, so that our temperature changes can be in correct order. This is 3x, because mass of cold water is 3 times mass of hot water. And this is going to be what? 20 minus 10. So that means 3x times 10 is the same thing as what? X times theta minus 20. I think we can make life easy for ourselves here. X, we take out x. You shouldn't actually do that. Just go to your next step. Theta minus 20 will be 3 times 10. So 30 is theta minus 20. What does that give you? Theta is 30 plus 20. And the temperature, the initial temperature of hot water will be gotten. It should be 50 degrees Celsius. The hot water was initially at 50 degrees Celsius. That's question 8. Question 9 says 300 grams of water at 90 is mixed with 100 grams of water at 30. What's the final temperature? That's your classwork. You did that yourself. Number 10. What mass of water at 100 degrees Celsius should be added to 15 grams of water at 40 degrees Celsius to make the temperature of the mixture 50? Okay? That means they are asking us hot water, what mass of hot water? Let's call it question mark, we don't know. You understand? At what temperature should the hot water be? 100 degrees Celsius. So initial temperature of hot water, 100 degrees Celsius, should be added to what? Cold water should be added to 15 grams of cold water. Mass of cold water, 15 grams. That's initially at what? 40 degrees Celsius. This one was initially at 100 degrees Celsius. To get a mixture that's at 50 degrees Celsius, I hope I got that right. Okay? Yes, to get a mixture of water that's at 50 degrees Celsius. So that's pretty simple too. Heat lost by hot water is equal to heat gained by cold water. Heat lost by hot water will be mass of hot water times specific heat capacity of water times change in temperature of hot water. Heat gained by cold water is mass of cold water times specific heat capacity of water times what? Senior, change in temperature of cold water times change in temperature of cold water. These multiplication signs are not compulsory, so let me throw them away. Change in temperature of cold water. So let's now put our values. We don't have the mass of hot water, so I'm going to keep it. Let me just write it as M. Seawater will take out each other. Seawater will take out seawater. So what you have left is what? M times delta theta for hot water is MC. Let me put this MH here, mass of hot water. Is MC times delta theta for cold water. Okay, this one will be M mass of hot water times 100. Hot water was initially at 100. So its change in temperature will be going down from 100 to 50. Mass of cold water was initially 15 grams. Its temperature will be increasing from 40 to 50. So the difference is 50 minus 40. You always do it to give you a positive answer. Take note of that. So what does that give you? Mass of hot water times 50 is 15 grams times 10. I hope that's clear. So you can do mass of hot water is 15 times 10 over 50 to get the initial mass of hot water. So what's the initial mass of hot water? Mass of hot water will be 150 over 5. What does that give you? 3. 3 grams. The mass of hot water should be 3 grams to get that final change in temperature. All right. That was question, I think, 10. Okay. Question 11. Water of mass 120 at 50 is added 20 grams and the mixture is calculate the temperature of the mixture. Same question. Do it yourself. You have to answer all these questions I'm skipping by yourselves. Number 12. How much heat is given out when a piece of iron of mass 50 grams and specific heat capacity 460 joule per kilogram per Kelvin cools from 85 to 25 degrees Celsius? Okay, we are looking for delta H, how much heat is given out. Piece of iron, what's its mass? 50 grams. Okay, 50 grams. Okay, its specific heat capacity, this is actually small letter I. Never mind, it's looking big. It's 460. Its specific heat capacity is 460 joules per kilogram per Kelvin. Be careful with units there. And it cools from a final temperature. It's cooling from what? It's cooling from a final temperature, from an initial temperature of 85 degrees Celsius to a final temperature of 25 degrees Celsius. So this is very simple. First thing you need to note here is that the unit of mass is in grams, but the specific heat capacity is given in joules per kilogram per Kelvin. You understand? So we need to first adjust this to 50 over 1000 to change it to 0.05 kilograms. I think we can now work with the values we have. Heat change is what? In this case, heat is lost because the iron is cooling. Heat loss will be mass of iron times specific heat capacity of iron times change in temperature. Mass of iron is 0.05 kilograms. Specific heat capacity of iron is 460 joules per kilogram per Kelvin, which is the same thing as per degree Celsius. You understand? Change in temperature is what? 85 degrees Celsius minus 25 degrees Celsius. So what does that give you? That gives you what? 0.05 kg times 460 times 460 joules per kg per degree Celsius is times what? Times 85 minus 25 is 60 degrees Celsius. So as you can see, units cancelling out. Degrees Celsius, we take out degrees Celsius. Kilogram, we take out kilogram. Everything left should be in joules. You now multiply 0. Delta H heat lost is 0.05 times 460. Joules is the only SI unit left, times 60. You put your values together, you get your answer in joules. It's as simple as that. Okay. A piece of copper of mass 30 grams loses 60 joules of heat. If the specific heat capacity of copper is 400 joules per kilogram per Kelvin, calculate the change in temperature. Okay. What number was this? 12. So we're on 13 now. A piece of copper, mass of copper, 30 kilograms, loses heat lost, 60 joules of heat. If the specific heat capacity, specific heat capacity of copper is 400 joules per kilogram per Kelvin, we are looking for the change in its temperature. Okay, first thing you need to know here is that inspect your quantities. Joules is in SI unit. This is in joule per kilogram per Kelvin, but this mass is in grams. So since this is in joule per kilogram per Kelvin, it must be made uniform with grams. So we have to change this to kilogram. 30 over 1000. we change it to 0.03 kilograms, so it can be used now in kilograms. You understand? Remember, heat lost is mass of copper times specific heat capacity of copper times delta theta. So if you rearrange, mass C mc times cc times delta theta is delta H. So specific heat capacity of copper is delta H heat lost over mass of copper. No, we are looking for change in temperature. So we make change in temperature subject to the formula. So every other thing left here, we go to the denominator. Exactly. So essentially, our change in temperature. Okay, this is the one that we want to make as subject of the formula. This is the one we are looking for. So these two, we go to the denominator side on the right. So will be MC times CC. Let me change that back to green. So what does that give you? Delta H 60 joules, mass 0.03 kilogram, specific heat capacity 400 joules per kilogram per degree Celsius or per Kelvin, whatever. So as you can see on the denominator side, this will cross this, it's normal there. Joules, we call joules, it's normal there. Degree Celsius will go up. Do you understand? So I think we have our answer. You'll be left with 60 divided by 0.03 divided by 400. You understand? When entering this in your calculator, be sure to use your calculator well. You should punch your calculator as follows. You do 60 divided by 0.03 divided by 400. That's how your calculator will give you the correct answer. If you make the mistake of using times here, it will be wrong because it's like taking this to the top, where it doesn't belong. So just use it the way I've done it here. This is how your calculator understands this fraction. Your calculator will do it correctly if you punch your keys in this order. Exactly. So it should be 60 divided by 0.03 divided by 400. And what does that give you? You will get your answer. Change in temperature in degrees Celsius. Delta theta. Exactly. Let me make this neat. Okay. That ends question 13. Let's go to 14. We are getting close to where we take a break. It says, how much heat is emitted when a body of mass 200 grams cools from 37 to 31 if specific heat capacity is 0.4 joule per gram per Kelvin? Okay. Mass of the body 200 grams. Specific heat capacity of the body 0.4 joules per gram per Kelvin or per degree Celsius. It's the same thing. So we could actually write per degree Celsius for this. Another thing is initial temperature 37 degrees Celsius. Final temperature 31 degrees Celsius. Heat lost, question mark. But we know heat lost is mass of substance times its specific heat capacity times temperature change. So in this case, our heat lost will be 200 grams times 0.4 times 0.4 joules per gram per degree Celsius times temperature change, which will be 37 degrees Celsius minus 31 degrees Celsius. So pay attention. This will give us 200 grams times 0.4 joules times 0.4 joules over grams degrees Celsius times 6 degrees Celsius. So units will cancel out unit. This cuts out this cuts out this. So everything you have left is just in joules. Let me remove all this cancellation. So this will be 200 times 0.4 joules times 6. You press your calculator, You get your answer in joules. That's the heat released or given out. That's number 14. Let's take 15. We need to be fast now that you know the basics. A piece of metal of mass 50 grams is cooled from what? 80 to 20. Calculate the amount of heat lost. The metal's material has a specific heat capacity of 450 joules per kilogram per Kelvin. Okay, mass of the metal 50 grams. Mass of the metal 50 grams. Initial temperature 80 degrees Celsius. Final temperature 20 degrees Celsius. So specific heat capacity of the metal 450 joules per kilogram per Kelvin. You can put per Kelvin here or put per degrees Celsius. So okay, heat lost is mass times specific heat capacity times temperature change. So what will our values be? I want to be sure. I didn't make me say 50, 80, 20, 450. Okay, that's right. So our heat lost will be 50 grams times 450. Okay, I think we are missing something here. 450 is in joules per kilogram per Kelvin, but the mass of the metal is in grams. So those are not uniform. I have to change my mass to something in kilograms. 50 over 1000 will change it to kilograms for me, and my mass is 0.05 kg. That's what I can use with 450 kilogram. 450 joules per kilogram per Kelvin. So I will change it to 0.05 kilogram times 450 joules per kilogram per degree Celsius. All right, they will not be able to cancel out each other because grams cannot cancel out grams. Grams cannot cancel out kilograms. Grams here will not be able to cancel out kilograms. So the units must just be made uniform. Times what? Temperature change is from 80 degrees Celsius to 20. We do bigger and smaller. What does that give you? That gives you 0.05 times 450 joules times 60. You understand? Degree Celsius change will cancel the degree Celsius change here too. Then everything is left in joules. You multiply, you get your answer. I can't do this for you anymore. I'm sorry about that, seniors. Number 16, am I right? 16, I think I'm right. A body of mass M. A body of mass M has a specific heat capacity S and a heat capacity C. Okay? If the temperature of the body changes by theta degrees Celsius, which of the following equations is correct? Okay? Body has mass M. So I'll just go ahead, write mass of body M, specific heat capacity of the body. Specific heat capacity of the body. What's it? I think small letter A. Am I right? The specific heat capacity of the body is S and the heat capacity C. So this is S. Heat capacity of the body. Let's space this. Its heat capacity is big C. Okay, the question says if the temperature of the body changes by theta degrees Celsius. Okay, temperature of the body, temperature change, theta. Okay, let me write this very well. They are just asking us, I think it's about heat change. The question is about heat change. Heat change can be expressed in terms of specific heat capacity or heat capacity. If you express it in terms of specific heat capacity, it will be mass of body times specific heat capacity times its temperature change. But if you express it in terms of heat capacity, you can put these two together. Mass times specific heat capacity is the same thing as big C, which is heat capacity. So I can write C times theta if I like. You understand? So that's the essential thing in the question. So that means you can either express your equation as this left or this right, because C is the same thing as what? Mass times specific heat capacity. Exactly. Heat capacity, which is big C, is the same thing as mass times specific heat capacity, which is small c. So mc delta theta is the same thing as c theta. But in this case, our c is written as small letter s. So that means you can write ms theta is the same thing as c theta. That's what our answer should be. Let's check. Ms theta is the same thing as big C theta. Okay. They've written the answer as C. Okay. Ms theta is the same thing as big C times theta. So if you cancel theta from both sides, I didn't notice that. If you divide theta from both sides, ms is the same thing as big capital letter C. So that's the expression we are looking for. I hope that is very clear. It's simple. Question 17 now. A copper ball of heat capacity 400 joules per Kelvin is heated from 20 to 100. Calculate the quantity of heat absorbed. You can do that yourself. That's an exercise. Number 18. A body of mass 40 grams loses 80 joules of heat. If the specific heat capacity of the body is this, calculate the change in temperature. That's also an exercise. We have done many questions like that. You did that yourselves. How much heat is emitted when a body of mass 50 grams cools from 80 to 20? Specific heat capacity of the body. That's also an exercise. We've done many questions like that. Okay, let's move on. 22,000 joules of heat is required to raise the temperature of 1.5 kilograms of paraffin from 20 degrees Celsius to 30. Calculate the specific heat capacity of paraffin. Okay, that's simple. I'll just hint you. Use delta H. Heat required is mc theta. So mc theta or mc delta theta. This is delta theta too, if you wish. Mc delta theta is what? Heat absorbed. So C is heat absorbed over m times delta theta. So that solves that problem for you for number 20 to get the specific heat capacity. Okay. How much heat is absorbed when a block of copper of mass this and specific heat capacity this is heated from this to this? 21. Also an exercise. I've taught you many questions like that. Use the same formula. Heat absorbed. Let me write a hint for you. Delta H is mc delta theta. You get your answer if you use this formula correctly. Make sure your units are corresponding. I think we can rest at 21. We'll continue in the next video. Make sure you do your exercises or your classwork. Seniors.